statistical paradoxes. We aren't going to spend a ton of time on this section, but it's actually a really interesting section. It's pretty short. I think it's only like 3 or 4 pages long, and the text, oh, it's like 4. So I would definitely recommend reading through it on your own, and I'm going to highlight some of the key takeaways from section 4.4. Here's our learning objective. So, some definitions. We're going to talk about false positives, false negatives, true positives, and true negatives. So, a false positive is an error in data reporting in which a test result improperly indicates presence of a condition such a disease. So, like, let's say I went and got a COVID test and I actually don't have COVID, but the test came up positive. That would be a false positive. False negatives would be an error in which a test result improperly indicates no presence of a condition. The result is negative when in reality it is present. So like let's say I went and got a COVID test and it came back negative and it was a false negative. That means they tell me I don't have COVID, but I actually do. And that could be pretty detrimental, right? If I don't think I have COVID, then I could not be quarantining, I could be going out, and that would be more dangerous not only to myself, not knowing I'm sick, but to those around me. So false negatives can be really detrimental. If I get a true positive, that would be a correct positive result. So I go get a COVID test and I test positive and I actually have COVID, so that'd be good. Then I know I'm sick, I can be taken care of, and I can make sure I quarantine from others. Next, we've got a true negative. That's a correct negative result. So I get a COVID test, and I don't have COVID. And the test says I don't have COVID. That would be a true negative. So true positives and true negatives, although if you were testing positive for a disease, that is very, very sad. What's really dangerous are false negatives. Because what if I tested negative for a disease such as cancer or heart disease, and I actually have that disease? That's why it's a false negative. That could be really detrimental to my health. And if it's something contagious, to the health of others. So let's take a look at this example 1. So suppose you're a doctor seeing a patient with a breast tumor. Her mammogram comes back negative. Based on the numbers in table 4.7, what is the chance that she has cancer? So it's important to note briefly that not all tests are 100% accurate, right? Like even the COVID tests, when you hear them talked about in the news, they're like 95% accurate, 90% accurate. So it's important to note that mammogram screening is 85% accurate, 85% accurately identifies those who have tumors. But my patient's really nervous, and even though her test came back negative, she wants to know what's the chance that she could still have cancer. So we have to look at our true positives and our false positives. So I have all the people who've gotten negative test results. That's going to be 8,430. So 8,430 women got negative test results. But she's concerned that she could actually still have cancer even though she's in the negative group. Well, she would be, if she did have a false negative, she'd be one of 15 out of 8,430 women, which would give us 0.0018. If we multiply that by 100, that's about 0.2%. So 2 out of 1,000. So the odds of getting a false negative, so getting a negative mammogram and actually still having cancer, are 2 out of 1,000. Let's take a look at another example where this false negatives and false positives can really have some more detrimental effects. So, all athletes participating in a regional high school track and field championship must provide a urine sample for a drug test. Those who fail are eliminated from the meet and suspended from the competition for the following year. Studies show that the drug tests are 95% accurate. Let's assume that 4% of the athletes actually use drugs. So let's say we have 1,000 sports participants. I am not into sports. Okay, so we have 1,000 sports participants. If 4% of them are actually using drugs, that'd be 0.4 times 1,000, which would give us 40. So I've got 40 on drugs and 960, the remaining out of 1,000, who are not on drugs. And I give them all the drug test, which is 0.95% positive. So if I take 40 times 0.95, that gives me 38. So 38, this is our true positives. So that'd be 38 high school athletes who are on drugs and tested positive. But that means I've got 2 false negatives. 2 were actually using drugs and tested negative. Now, that means 2 got away with it, but let's see how that affects the 960 who were not on drugs. Again, this test is 0.95% accurate. So if I take 960 times 0.95, that's going to give me 912 of those who got true negatives, right? They are not on drugs and they tested negative. But that means I have 48 who get false positives. So what if I want to know what fraction of the athletes who fail the test are falsely accused and therefore suspended without cause? So we need to take all the athletes who fail the test, which would be these 48 and these 38, right? They failed the test, so that gives me 48 plus 38, which is 86. So I have 86 people who tested negative, but 48 of those are false positives. So 48 out of the 86 were not actually using drugs. That's 56%. So 56%, that's 0.56, times 100 would give us 56%. So 56% of participants who tested positive for drugs were actually suspended without cause. And that's over half. So that's one of the compounding effects of false negatives and false positives, and why it's called a statistical paragraph. So if you want to go ahead and read through this section, there's some interesting examples on polygraphs, drug testing, and some more medical examples.